Hey everyone, welcome back to my YouTube channel. So today we'll be solving the February-March 2018 physics paper, specifically paper 4 variant 2. So let's get on with the video. So the first question asks us to define acceleration. And acceleration is the rate of change of velocity. So whenever you see the word rate, you think of time. Okay, so let's look at an example. Say there's a car that starts at 20 meters per second. So the starting point is at time 0. So t is equal to 0. And it continues at 20 meters per second for a total of 1 second. And then after that, it moves on to say 21 meters per second. And then another second passes and it's moving at a speed of 22 meters per second, right? So that's a total of 2 seconds, right? But if you notice, we're increasing by 1 meter per second every second, hence the squared, right? So then that's your acceleration. It's the change in the velocity with respect to time. So you can write this, or you can actually write the equation. Both are acceptable. So acceleration is the final velocity minus the initial velocity over the total time. So our final velocity is 22 meters per second. Initial is 20 meters per second over the total time, which is 2 seconds. That would be 2 over 2, which is equal to 1 meters per second squared. Anyways, let's move on. So we're looking at this speed time axis, right? So the car starts from rest. So the car starts from rest from time t is equal to 0 to time 15 seconds. The car has a constant acceleration to a speed of 28 meters per second. So we have a speed time graph. I'm going to tell you this. So basically, the slope of this graph is the acceleration. This is the acceleration. Now, if we want a constant acceleration, then that means that the slope should be constant. So it's not like a curve that's upwards or downwards, it's a straight diagonal line. If it's deceleration, so our acceleration is decreasing, then it would be a slope drawn this way. The reason it's not a horizontal line, that would just simply mean that the speed is constant, because we're looking at the axis here, which is speed. So speed is constant, that would be a straight line, right? So for example, at 20 meters per second. And if we try to calculate the slope, so you know how there's the equation of a line, which is y is equal to mx plus b. You have m here. So in the case of a horizontal line, say for example this is 220 and this is the point 0, 20. So these 2 points, right? Let's try to calculate that. So change in y over change in x. So that's 20 minus 20 over 2 minus 0. That's 0 over 2, and 0 divided by anything is 0. So that means you're not accelerating at all, and hence that's why it's not a horizontal straight line. Instead, it's a constant acceleration. We're constantly moving at an acceleration, for example, at 1 meters per second squared. But anyways, you don't have to do any calculations for this question. All you have to actually do is find your point 0, 0 and the point 15, 28. So time 15, which is right here, and 28 right here, and then create a straight line, which I have already done. Now we move on. So from time 15 to 32, right? The car has a constant speed of 28 meters per second, which we showed you is a horizontal line. So just very straightforward. So from the time 32 seconds, the car has a constant deceleration of 2 meters per second squared until it comes to rest. So with this part, now we actually have to do a calculation. So let's calculate. Okay, so we have these 2 points, 32, 28, x, and 0. We don't know what x is, we don't know where it's stopping, but we do know that the value of y, or speed in this case, is 0. Okay, so we know that m is equal to y2 minus y1 over x2 minus x1. So we're going to label these as x1, y1, x2, y2. We know what m is. M is 2, but it's not 2, it's negative 2 because it's decelerating, right? Deceleration. So negative 2 is equal to 0 minus 28 over x2 minus 32. We move this here, so negative 2 times x2 minus 32 is equal to negative 28. So negative 2x2 plus 64 is equal to negative 28. Negative 2x2 is equal to negative 28 minus 64. So negative 2x2 is equal to 92. So then x2, or negative 92, sorry. So x2, divide the whole thing by negative 2, will give you 46. So we find 46 here, and we draw our line from this point, 32.28, all the way to 46.0. And that's it. So from time 15 seconds to time 32 seconds, the path of the car is part of a circle. So for this motion, state the direction of the resultant force of the car. So when we're moving in a circle, the force is acting towards the center of the circle. What happens to the velocity of the car? Obviously, the velocity is continually changing its direction. So you know how there's speed and there's velocity. The difference between them is that velocity also involves the direction. So now the speed is constant, for example. Well, actually, it is constant between 15 and 32 seconds. It's at 28 meters per second. However, its direction is changing. So if you have your car right here, all right, this is the direction of the velocity at first. Say the car comes onto this side now. This is the direction of the velocity. So the direction is changing, but you'd notice that the resultant force is towards the center. It's not changing. So here, the direction of the velocity and the direction of the resultant force are at 90 degrees. All right, so let's move on. That's all for question 1. So for question 2, a force is used to move an object from the Earth's surface to a greater height. Explain why the gravitational potential energy of the object increases. Okay, so because gravitational potential energy is the work done by the force, right? So gravitational potential energy we know is mass times gravity times the height. And since height has increased, so would the gravitational potential energy. That's because they are directly proportional, right? So even thinking about it really like generally, you have your Earth right here, and say there's an object that's going further away. That would take more work for you to bring it back inwards because the gravitational force acts towards the center of the Earth, right? That's why you have satellites orbiting the Earth, because it stays towards the center. It's just like the movement of the car in a circle. So that would involve definitely more work. You can mention either one. You can say because of this at the top, or you can say or you can mention the formula and mention how the height is increasing. Okay, so figure 2.1 shows a train moving up towards the top of a mountain. The train transports 80 passengers. The train transports 80 passengers, each of average mass 65 kilogram, through a vertical height of 1,600 meters. Calculate the increase in the total gravitational potential energy. We know what it is, so mass times the gravitational mass times the gravitational acceleration times the height. So the mass is 80 times 65 because there are 80 people and each of them weighs 65 kilograms on average, times 10 meters per second. This is a number that you guys should have memorized. So the gravitational acceleration on Earth is 10 meters per second squared times the height will give you this value. Now you'll notice that the final answer is given to 2 significant figures and not 3. That's because the numbers we're working with all are given to 2 significant figures, right? So then you should leave your final answers to 2 significant figures. Now, when we're using this value again in this question for its calculation, make sure to use the full value. We don't want to prematurely round because that will end up making us get the wrong answer, right? So use 8.32 instead of 8.3 in this question. So the engine of the train has a power of 1500 kilowatts. Pay attention to the units. The time taken to reach the top of the mountain is 30 minutes. Calculate the efficiency of the engine in raising the 80 passengers 1600 meters to the top of the mountain. So we know that power is energy over time, or the rate of change of energy. So we know what the power input is. It's 1500 kilowatts. But what's the output, right? So based off of the energy here, the total increase in the gravitational potential energy of the passengers divided by the time. So the time has to be given in seconds, so change 30 minutes to seconds, so multiply by 60 will give you this value, and that's joules per second. So that's the power output. Efficiency would be the power output divided by the power input times 100. Why it's output over input, you can think about your tests, for example. So the test is out of, say, 30, and you got 28. So that's how it works. That would be your input, right? And then this is your output. Alright, so if you place that in your calculator, you get 3.1%. So power input, make sure you, like I said, pay attention to the units. It's kilowatts, so the answer is not, so it's not 1500, it's 1,500,000, right? So just be careful. Alright, so for question 3, complete the statement by writing in the blank spaces. The moment of a force about a pivot is equal to the force multiplied by the perpendicular distance from the pivot. So moment, force times distance, and this is just the perpendicular sign, right? Okay, so figure 3.1 shows a horizontal rod of length 2.4 meters and weight of 160 newtons. The weight of the rod acts at its center. The rod is suspended by 2 vertical ropes, X and Y. The tension in each rope is 18 newtons. So state the name given to the point at which the weight of the rod acts. That's the center of mass. Very self-explanatory. It's the center of where the mass of the rod is. Okay, so calculate the mass of the rod. We're given the weight, but not the mass. And the weight is, in order to find the weight, the formula is mass times the gravitational acceleration of that planet. So for Earth, it's 10. We want to find mass, so what we're going to do is divide the whole thing by the gravitational acceleration. So 160 newtons divided by 10 meters per second squared will give you 16 kilograms. So the rod is in equilibrium. Using data from figure 3.1, explain why. So due to the upward and downward force being equal in magnitude, there's no resultant vertical force. So how can we show that? Let's see. The upward force is 80 plus 80, which is 160 newtons, and the downwards is also 160 newtons. So they cancel out, right? So the rod is not moving up or down, but the rod, for example, could be rotating clockwise or anti-clockwise, right? Also, there's no resultant moment about any point. This is due to the clockwise moment equaling the anti-clockwise moment. So the force times distance. 80 times 1.2 is equal to 96. So we're going to use the center right here as the point where it's supposed to be pivoting from. But let's see. We have a force of 80 and a distance of 1.2, so that's halfway between 2.4. And that's equal to 96, but then on this side it's also equal to 96. So yeah, we're not actually moving clockwise or anti-clockwise. Say for example this was 100 newtons. We might be pivoting a bit towards this side, so it could be slanted like so. But since it's equal, then it's in equilibrium and we don't have to worry. So mentioning these 4 things, so mentioning that it doesn't move up and down, that it doesn't rotate, and then giving your reasoning behind it will give you the total 4 marks. Okay, so on to question 4. So figure 4.1 shows a cold plastic spoon that has just been placed in a hot liquid in a cup. So describe in terms of molecules why the temperature of the whole of the spoon increases. Now let's speak generally about temperature. Temperature is the measure of the average kinetic energy of the particles in an object, right? So the more kinetic energy the particles in that object has, the higher the temperature, right? So when temperature increases, the motion of these particles also increases. Okay, so molecules of the hot liquid collide with the surface of the spoon. Right here, they're having a blast, right? All over the spoon, right? Okay, so energy slash heat to the they transfer energy slash heat to the molecules of the spoon. Vibration of the spoon's molecules increases, right? And hence the temperature of the whole spoon increases as well. So the more it vibrates, or in other words, the more kinetic energy it has, the greater the temperature would be. Now, the plastic spoon is replaced by a metal spoon. Describe an additional process by which the temperature of the whole of the spoon increases. So the molecules of the hot liquid also transfer that energy to free electrons in the spoon. And these free electrons move through the metal. So if you look at a metal, right, we have its atoms. So say, for example, this is magnesium, right? It has a sea of free electrons. Just vibing out here, right? So, so it has that sea of free electrons, whereas the plastic spoon did not. So hence that's why that energy can also be transferred to the free electrons and not just the atoms or molecules. All right, so the cup contains 150 grams of liquid of a specific heat capacity, 4.2. When the cold spoon is placed into the hot liquid, the temperature of the liquid decreases from 80 to 56. So calculate the loss of thermal energy from the liquid. So the energy is given by this formula, mc delta T. So the mass, which in this case is 150 grams, times the specific heat capacity, which is 4.2. So this is something you should pay attention to. So you have grams here and you have grams here, so you know you have the right units. So 150 times 4.2 times the final temperature minus the initial temperature. That will give you negative 15,120 joules. But if you notice, again, we're working with two significant figures, 2, 2, 2, 2, right? So we're going to give it to two significant figures as well, so that's negative 15,000 joules. Here it says energy loss, so we don't have to place the negative sign. The negative sign just tells us that there was energy loss, but if they're telling us what is the energy loss, you don't have to give that negative sign. It's kind of like acceleration and deceleration. So you can say decelerates by 2 meters per second, or you can just say -2. So something that I've noticed in these papers is that they don't give you the units at the end. So that's, I guess, something to see whether or not you guys truly understand or not. And in this case, you can write it as 15,000 joules or 15 kilojoules. Either way, it's correct. Alright, so for question 5, it shows the apparatus used to observe the motion of a smoke particle. The motion of a single smoke particle is observed through the microscope, and they're asking us to sketch its path. So just start anywhere and make it very random, but straight path with straight lines, and that's it. And the reason this is happening is because of Brownian motion. So the air molecules move in random directions, right, which collide with the smoke particles, which causes a change in their direction. It's kind of like bumper cars. You know, you're just playing around, and when you keep hitting each other, you are moving. And bumper cars usually move in a straight line too. So you're moving this way, you get bumped. You're moving that way now, and then you're moving this way and that way, and so on. But yeah, this is called Brownian or Brownian motion. I'm not really sure how to pronounce that. Alright, so for part B, a tennis player is practicing by hitting a ball many times against the wall. The ball hits the wall 20 times in 60 seconds. The average change in momentum for each collision with the wall is 4.2 kilograms meters per second. So calculate the average force that the ball exerts on the wall. So unit of force is newtons, which is equal to 1 kilogram meter per second squared, which I mentioned earlier, right? So we have 4.2 kilograms meters per second, And we have second. How do we get it to meter? How do we get it to second squared? We simply divide by seconds. So 4.2 kilogram meters per second, right? Times 20 over 60 seconds. And when you're multiplying, you simply go across. So 4.2 times 20, which is 84 kilograms meter, and then 60 seconds. So 1 times 60 is just 60 seconds squared because there's 2 seconds. So that gives us the unit, and if you simplify, that gives you 1.4. But we can do this for the proper way. So force is mass times acceleration, and we know that acceleration is the final velocity minus the initial over time. So m times v minus u over t, right? Impulse is mass times the change in velocity, which is, so impulse is basically the change in momentum. So that's what it is, right? So we can simply say that force is the impulse divided by time. We have the impulse, which will end up being 4.2 times 20 over 60, which is 1.4 newtons. The reason we do 20 divided by 60 is because we're trying to find out how many times he's hitting that wall in 1 second. So 20 divided by 60 is 1 over 3. So he still hasn't hit the wall. He's 1/3 there towards, he's getting there. He's 1/3 there to actually hitting the wall. So you end up getting 1.4 newtons. Alright, so for question 6, this is something very straightforward that you need to memorize. So A would be infrared, B would be ultraviolet. So if A is infrared, then you know that the ultraviolet would be on this side, because infrared would have the red light next to it from the visible light spectrum, so then the violet would be on this side. Then you have X-rays and then gamma rays, and that's it. So for this question, a source emits visible light, shows a ray of red light from the source incident on the face XY of a glass prism at point S. So we're asked to calculate, so the angle of incidence is 35 degrees. The refractive index of the glass for the red light is 1.5. So we want to calculate the angle of refraction. So this angle right here in the glass at S. So if n is 1.5, so actually before we substitute the values, let's rearrange the formula to make r the subject, right? So n is equal to sine I over sine r. So that would be sine r equaling to sine I over n. So r is equal to the sine inverse of sine I over n. So that's the sine inverse of sine 35 over 1.5, which should give you 22 degrees. And remember the two significant figures. So on figure 6.2, draw the refracted ray at face xy and the ray emerging from the face xz. So xy and xz of the prism, and label this ray r. So r is in red, so we're going to just label it right here. Okay, so we have our normal. We're going to create the angle. You don't have to be very precise in this case, as long as it's significantly, or it's obvious that this angle is smaller than the incident angle. So this should be 22 degrees from the normal. So that's your red line, and then you create another normal on this side, and normal is just going to be 90 degrees to the surface. There you go, it's perpendicular to the surface. So you're going to move out, and of course that's going to have a greater angle compared to what was on the inside, mainly because the refractive index of air is smaller than that of glass. Okay, and now we're asked to repeat the same thing, but repeat it for the blue light. So the blue light would be the same thing, it's just going to be underneath the red. It gets refracted more than the red light. And the reason why the blue light ends up underneath the red light is because it has a shorter wavelength. And because it has a shorter wavelength of light, it's slowed down even more, and so it experiences more bending. So, shorter, slower, more bending. All right, so let's move on. So for question 7, the speed of light wave. For question 7, the speed of light wave in air is 3 times 10 to the power of 8 meters per second. The refractive index of water is 1.33. Calculate the speed of light in water. So the general formula is N is equal to C over V. C is the speed of light and V is the speed of the medium. So in this case, it's water. So let's isolate for V. So N is C over V. So then that would be C over N. You can think of it as a little triangle, C and V, so then V would be C divided by N. So 3.00 times 10 to the power of 8 meters per second. You notice that it's 3 significant figures, or to 2 decimal places. And then here you have 1.33. That should give you this answer. Now, the mark scheme is given as 2.3, but I believe it should be actually given as 2.26 times 10 to the power of 8, simply because if we're trying to stay consistent with the number of significant figures or decimal places. But anyways, you still get the marks either way. Figure 7.1 shows parallel wavefronts of a light wave in air incident on a boundary with a transparent plastic. So we have the direction of the light wave moving this way, right? So that's perpendicular to the wavefronts. So draw the position of the 4 refracted wavefronts in the plastic. So all we have to do here is create the normal, which is, well, perpendicular to this line right here. So we have this angle over here at this one right here. So as soon as the wavefronts come in contact with the transparent plastic, they're going to move more slowly, and so it's going to bend more. It's going to bend towards the normal. So this angle should be smaller than this one, right? So if that's the case, then we draw these out like so. They have to be parallel to each other. And so then they asked us to draw an arrow to show the direction of travel of the refractive wave. So the wave in this case, like we said, 90 degrees. So grab your protractor and form a 90 degrees like so. This is the direction of the wave. And then label the angle of refraction R of the light wave. So angle of refraction would be right here. That's R. And there you go. So for question 8, the lamp of a car headlight is rated at 12 volts and 50 watts. So calculate the current in the lamp when operating normally. So power is given by current times the voltage. So then current is power divided by the voltage. Power is the 50 watts divided by the 12 volts, gives you this value. Again, 2 significant figures, so 4.2 amperes. A car is driven at night. In a journey, the total charge that passes through the 12-volt battery is 270 coulombs. Calculate the electrical energy transferred. It's given through this formula. So E is equal to Q times V. So the electrical charge is 270 K. So K is 1,000. So 270 times 1,000, or 10 to the power of 3, times 12, which gives you this value. Or you can write out 32,000 kilojoules. So the fuel used by the car provides 3.6 times 10 to the power 4 joules per centimeter cubed. We're asked to calculate the volume of fuel used to provide the energy calculated in BI. So we have this. This is like the total, like we said, the inputs before earlier, or your test score. And this is your output, or the mark that you got. So make sure to keep the units consistent. So here it's given in joules, so provide the one in joules and not the kilojoules. Place that in your calculator and you'll end up getting 90 centimeters cubed. If you're not sure, even if you didn't know like this is how it's calculated, you can again look at the formula. You can again look at the units. So you have joules divided by joules over centimeters cubed. So that's joules times centimeter cubed over joules. So when you divide, you can also multiply by its reciprocal and it will give you the same answer. So that's over 1. So joules times centimeter cubed over joules, that will just cancel out because anything over itself is equal to 1. So joules over joules is equal to 1. So that gives you your answer in centimeters cubed. So that's how you know you're right. So figure 9.1 shows current potential difference graphs for a resistor and for a lamp. The potential difference applied to the resistor is increased. Tick the box that indicates the effect on the resistance of the resistor. So resistance is the voltage divided by the current. Okay, so it's this slope right here that's equal to 1 over R. And why is that? Because when we look at slope, it's delta y over delta x. So this is your y-axis, this is your x-axis. So that would be current I divided by V. But R is V over I, so that's its reciprocal, so that's 1 over R. Anyways, you notice here that the resistance is constant, it's not changing, it's not, like we said, a curved line, instead it's a straight line, a straight diagonal line. So now the potential difference applied to the lamp is increased. What's going to happen? The resistance would also increase. Why is that? It's because the voltage, look at, it's gradually decreasing, right? So the current, so basically the voltage and the current aren't increasing at the same rate. So the voltage is increasing more than the current is. So in that case, the resistance would increase. So we have a larger number getting divided by a smaller number would give us a greater resistance, right? All right, so the potential difference across the lamp is 6 volts. Calculate the resistance of the lamp. So so the resistance is going to be 6 divided by 4.4, which is 1.4 ohms. How do we get 4.4? We find it right here. So we go to the lamp at 6 volts. We move up, and right here it's at 4.4. Not 4.2, 4.4. Be careful of the scale, so pay attention to that. Alright, so let's move on. So for part C, the lamp and the resistor are connected in parallel to a 6-volt supply. So calculate the current from the supply. So if we have something that's connected in parallel, the current is obviously going to split, right? So the current is the initial current, some of it is going to go here, some over here, some down here, some here. But if you add them all up, it'll give you your original current again, right? So the current in the lamp at 6 volt, we found that to be 4.4. And if you go up at 6 volt, that's at 4 amperes for the resistor. Right, so the current from the supply would be the addition of both. So in this case, we only have these two. So we have here a resistor. This is definitely not the symbol. And we have a lamp that's right here. Okay, so the lamp and the resistor are connected in series to another power supply. The current in the circuit is 4 amperes. So calculate the total potential difference across the lamp and the resistor. So the potential difference across the lamp. So if we're in series, okay, we have your resistor, your lamp. Please ignore that, and your power supply, right? So when you have something in series, then the current is constant. However, the voltage is being divided. So here the voltage is the same, right? At 6 volt. But then in series, the current is the same as the opposite, but the voltage is split. So we find the potential difference, which we can find from the graph. It would be 4.9 for the lamp and 6 for the resistor. Add them up, and that will give you the total potential difference. In this case of the power supply, which is 10.9 volts. All right, so question 10. For question 10, we need to state 3 factors that affect the size of the deflection of the galvanometer. So that would include the strength of the magnetic field, the speed of the movement of the wire, how fast you're moving it up and down, the length of AB within the field. So that's actually really important. So it's just not the length of the wire, it's whatever length of AB or the wire that's actually interfering with the field, specifically the magnetic field. So we move on. The primary coil, so this is a transformer, has 8,000 turns and an input of 240 volts. The secondary coil has an output of 12 volts. So we're trying to find the number of turns. So that's Vp over Vs, so the voltage of the primary over the voltage of the secondary is equal to the number of the primary of the number of the secondary. You can switch it up. You can do Vs over Vp. That's totally fine as long as you stay consistent and it becomes Ns over Np. Or you can also try Vs over Ns, so secondary on one side, and you have Vp over Np. Either way, you'll still get the same answer. So we want Ns, and that is, so if you look at it from here, Ns is equal to Np divided by Vp over Vs, which is the same as Np times Vs over Vp, which is the reciprocal. So Np is 8,000 times 12 over 240, which is 400 turns. Alright, so let's move on. So a circuit containing a resistor is connected to the terminals A and B. A direct current is required in this resistor, so that's pretty important. So we have a galvanometer right here, right? And we have the wire AB. And then we connected, and then a circuit is connected to the terminals A and B. So you have A and B here, we connected this circuit. It has a resistor, so we're going to place the resistor right here. That's a really bad drawing for a resistor. And in order to make it a direct current, we do need a diode, so we're going to place a diode right here. And that's it for this question. Alright, so let's move on. So to ensure the safety of workers in laboratories where radioactive sources are used, describe how radioactive materials should be stored. They should be stored in a box with lead walls, because if you look at B, gamma rays are the ones that have the largest range in air, several kilometers, and they're absorbed by thick lead or very thick concrete, so we do need lead walls, right? So we don't get affected by the radioactive waves. So how should they be handled? You can mention any of the four. So with long tongs, a remote control device, while wearing lead gloves, or while wearing a lead suit. So let's look at the nature. So if it's an electromagnetic radiation, then you know it's a gamma ray. That's the type of emission. If it's a helium nucleus, you know it's an alpha particle. If it's an electron, then you know it's beta. So its range in the air. The range for gamma is several kilometers, whereas for alpha it's a few centimeters, and for beta it's a few meters. You can say a few centimeters, or you can say up to 10 centimeters, and here the same thing, you can say or up to 10 meters. So the gamma rays are absorbed by thick lead, or you can say 30 centimeters of thick lead, or very thick concrete, or 3 meters of thick concrete, or very thick concrete, right? Alpha is absorbed by 0.2 millimeters of paper, and beta is absorbed by thin aluminum, or you can say 2 millimeters of aluminum. So for this question, notice that there is a difference in the proton number and the mass number. So the number of protons decreases by 2 and the mass number decreases by 4. That's a helium atom, which is the same as an alpha particle. And for part 2, you notice that there is an increase in the proton number. So you know that's a beta particle. So basically the neutron, which has a charge of 0, is broken down into a proton and an electron. So the overall charge is still 0. So because 1 plus negative 1 is 0. And there you go, an increase in proton number. That's 16. However, the mass number, so the number of protons and neutrons, is still maintained. That's why the 32 is the same. But anyways, that's all for this paper. I hope that was helpful, and I'll see you guys next time. Bye bye.